Hello, everyone. Thanks for coming to my talk. So a bit about me first. So I'm Quentin Warnant. I'm a senior rendering engineer at Rare. I joined in 2021. We're based in the UK, in the middle of it, and we've just celebrated our 40th year of making games. Some of the games you'll recognize, like Sea of Thieves, GoldenEye, Banjo-Kazooie, and many, many more. We are also part of the Xbox Game Studios. And prior to that, I worked on mobile games where I contributed to games like in the Sonic franchise and the Warhammer titles as well. And these days, my main interests lie in GPU-based simulations and performance optimizations. Today, the topic of my talk is around R&D work that I've been leading at Rare to make static meshes like vines fully dynamic and interactive. So I'll start off by showing what the effect looks like, and then I'll deconstruct it and describe it piece by piece. It's a physics simulation of an aggregate of vines, and it runs in real time with support for interactions. You'll observe that it receives gusts of winds and that it collides with both the environment assets and animated characters. When the character walks through the vines, you'll see that it splits and wraps around their body. The goal of a system like this is to make our game's world feel more interactive by having more dynamic environmental elements that react to both the player and non-player characters in the scene. So let's have a look at the components in play to make an effect like this work. The system is built using a variety of native Unreal features. We use Niagara to run compute shaders with simulation stages on a grid 2D collection, and use both built-in and some custom Niagara data interfaces. Then we use Nanite meshes and efficiently deform them to using a joint-based animation technique. We integrate world forces like winds of gusts to grant the effect in the rest of the dynamic world. And finally, we also support collisions with the world sign distance field and animated characters. At the end, I'll also talk a bit about debugging tools and performance. So I'm aware that maybe not everyone is aware of position-based dynamics or how it works, so I thought it would be useful to go through a quick primer before I go any further. So it's a physics solver algorithm. It handles the integration of forces upon nodes, and it tries to enforce constraints between nodes. So as an example, for vines, a natural representation is a chain like these, where nodes are represented by circles, and each is connected to the previous, to the next one from top to bottom using these chains. In general, nodes can be thought of as particles with properties like positions and orientation, and constraints are applied to the interconnection between nodes. For example, here we have a length constraint. It defines the desired length between two nodes connected to each other. And the constraint will move the nodes either away or towards each other to satisfy the original length. Then you get angle constraints that control the maximum angle between a series of nodes. This can be useful to avoid unrealistic bending angles on materials like ropes. You can get volume constraints. They can be useful to retain the volume of a shape when you push or pull a node. We can look at collisions with the environment and characters as another type of constraint. Nodes shouldn't be penetrating in the surface of these objects, and if found to do so, we should push them out until they are lying at the surface. These are just some of the most obvious types of constraints, but it's actually pretty straightforward to add some more bespoke ones that make sense in your particular game. The iterative physics solver algorithm performs two steps. First, it integrates the internal and external forces. The internal forces is the velocity that already existed in the simulation from a previous frame. And the external forces usually include gravity, but it can be anything. So in our case, we also include wind. And then the second step is to enforce the constraints. So this is done through multiple iterations, as it's hard to compute the final position otherwise. One thing to note with position-based dynamics is that we're not storing velocity properties on the nodes. Instead, we keep the position value of the current and the previous frame and compute the velocity from their difference. This is meant to keep the simulation more stable. In our implementation, we only use length constraints between two nodes along a chain and also support collisions. So looking at a length constraint solver, this is how node positions are iteratively refined. Let's say this is our starting point. Then we integrate some forces. So gravity will pull the nodes down. And let's say there's some wind that has also pushed them towards the right. Note that I pinned the node at the very top. Let's say we've attached it to a wall or a tree. So now we start the iterative process and handle the first length constraint. We can notice that the current length is longer than the original length. So the difference is the amount that we need to correct. Given that one of these nodes is pinned, we'll just move the other nodes towards the node at the very top by that entire correction distance to satisfy that desired length. Next, we'll handle the second length constraint, and as this is also exceeding the desired length, but since neither of these nodes are pinned, we actually will spread the correction length evenly between the two nodes and move both a bit towards each other to satisfy that length constraint. And we keep doing this until we reach the end of the chain. Now, if you've noticed, the second node in this chain was moved down as part of this solving the second constraint, therefore doesn't satisfy the initial length constraint at the top anymore. So this is where the iterative algorithm progressively corrects the positions further and further towards the correct solution. So again, we calculate the difference between the current length and the desired length and move the unpinned node to satisfy the intended length before moving on to the next constraint and so forth. Eventually, with enough iterations, all the constraints will be satisfied. And I'll show the original configuration of the chain behind here, so you can see that the length was maintained whilst the forces were successfully applied. In practice, we set a fixed number of iterations. That seems to work for this effect or this asset. And it's worth noting that the longer a chain like this is, the more iterations we may need to converge to a correct solution. But it's also a dial that can be tweaked to reduce the cost of the simulation if we are happy to forgive a bit of stretching. So you might have noticed by now that this is a serial process, which is a bit of a crime on a GPU since it's built for parallelism. Unfortunately, that is the nature of the solver. We need to solve the position of the previous node in order to place the next node in the right place. But given that there's no interdependencies between different chains, we can run this solver for many chains in parallel, which is where the GPU excels. So let's come back to our own implementation, and I'll go over some details now. First, let's have a look at our Vine mesh. We bake some metadata into the vertex attribute channels. The vertex color's red channel will represent the total length of a vine as a fraction of the entire object's bounding box. In the green channel, a gradient will be representing how far along a particular vertex is located along that vine. And we then also store a pivot location at the very top of the vine across the UV1 and 2, here highlighted in orange. There are a few more channels displayed here that are part of our larger material setup for foliage, but they're beyond the scope of this talk. With this data, we know where each vine starts. These points at the top, and how long it is, so we can allocate the PBD nodes along them to represent a chain. The amount of nodes over a given distance is configurable, and it's a value that again balances cost and fidelity. The physics solver is implemented with compute shaders in Niagara, and the PBD node properties are stored in a grid 2D collection. I'm not actually using any Niagara particles except for visual debugging like here. Once the simulation is ran, the output is a position, normal, and tangent for each node, which are then written into different rows of a render target. The Vine mesh material has then the same render target bound and samples it to offset the location of the vertices based on corresponding nodes that they are nearest to. The same way you can imagine with skinned mesh vertices will move based on nearby joints on a CPU-driven animation. We use this technique in a few of our effects and refer to it as textured joint animations, or TJA. And finally, the results of this deformation is then fed into the material's world position offset property. Now let's have a look at the simulation setup in Niagara. During the emitter spawn stage, we initialize a few properties. The Foliage Niagara data interface is custom made and is used to read the mesh vertex data shown earlier. We also initialize the rigid mesh collision query Niagara data interface, which is built in Unreal and is used to find collisions with characters. Then we count the number of unique chains in the mesh and the number of nodes that are required based on the length of each of those vines, and create and initialize the grid 2D collection in which we will store the PBD node data. We also create and initialize a couple of render targets. One of them is to represent the output of the simulation, and the other one is for some metadata for each vine. A few more settings then to control the simulation. And finally, we use another custom Niagara data interface called Material Instance Dynamic, which allows us to set a few global parameters on the material. More on that later. The emitter update stage is very simple. We just sample the current wind direction and query the rigid mesh collision Niagara data interface to find the current relevant actors within the bounds of the emitter. There's also a disabled burst spawn stage for particles visible here. This is just for debugging again. The simulation is not using particles. So after the emitter update stage, we have a few simulation stages. First, the initialization of the grid 2D collection in which we'll store the PBD nodes with default values. We do this only once. Then we initialize a metadata render target, which I'll get back to in a slide or two. Then we run the PBD solver. And finally, we write both the current frame and previous frame values of the nodes, position, normal, and tangent, to the node's data render target. The PBD solver logic looks a bit like this. First, we dispatch one wavefront per chain. Each thread represents a PBD node. Each node loads its data into the grid from the grid 2D into group shared memory. If you're not aware, that is local memory on the GPU. Then each node samples the wind noise function and stores the results also in group shared memory. And then the first thread will run the serial iterative solver over group shared memory for all the nodes. That looks a bit like this. First, we integrate the physics forces, then we loop a number of times over the constraints, and finally resolve the collisions. Once all this work is done, all the threads resume work and retrieve the updated positions from group shared memory to write them back into the grid 2D collection. Then we can compute the normal and tangent from neighboring nodes, and finally write these to the output render target. And practically speaking, all of this is written in a custom HLSL node in Niagara, and the iterative solver part is actually located in a header file. That has made it more manageable to write the code, and also it's more easily testable. If you're curious about shader code testing, I can recommend my colleague Keith Stocksdale GDC 2024 presentation on the subject. The downside of using an external header file is that Niagara actually parses the text in the custom HLSL node and only populates the Niagara data interface functions in the final shader file that have been called in there, not the ones that have been called in the external header file. So a workaround for that is to do some dummy function calls in the custom HLSL node so that the function will be populated and we can call them later. The compiler should ignore these dummy function calls as long as we don't use their results. And sometimes it's also viable to find and include some other HLSL headers that the Niagara data interfaces would call themselves, or forward declaring some functions, but it's something that I guess could be improved a bit in the future. Let's look at the simulation data next. In terms of data flowing through the system, we've got a grid 2D collection, which has an entry for each PBD node, and that holds the current position, previous position, normal, tangent, whether the node is pinned or not, whether it collided against something last frame, and its mass. We then have two render targets, which the Niagara simulation writes to, and the material reads in. The simulation results render target with 3 rows for each PBD node, for node position, normal, and tangent, and then repeated to hold the previous frame values as well, so we can compute correct motion vectors. In this example, we have 3 vines, one with 2 nodes in blue, one with 4 nodes in orange, and finally one with 3 nodes in purple. And then secondly, we have the metadata render target. We initialize this texture only once, and it's very small, 2 columns, and it holds in the first column the node index range for that given chain, and its chain length as well. And then in the second column, the branch pivot. This is all we need to figure out the location of a vertex based on the simulated node positions. We first identify which chain a vertex belongs to by looking at the vertex UV data. Then we assemble the chain branch pivot, and then we look through the metadata render target to find an entry with the same branch pivot in the right column, and in the left column we'll be able to get the node index range for that particular chain. As I mentioned, there's a chain length in that column as well. If we look at how far a vertex is from the pivot and divide it by this chain length, we'll get a normalized distance value within that chain. And that value is then used to interpolate between the node index range in the render target on the left-hand side to sample the position, normal, and tangent values. So as an illustration, take this chain, and let's say we've identified it was part of the second vine. I'll visualize a triangle on the vine mesh, and I'll also let's focus on that orange vertex highlighted with a circle. If we put that in the range of the second chain node data, we can then sample all of the rows to get an interpolated value for that row, for that vertex. Next, let's look at the material. One of the restrictions we have with Niagara is that we can't render nanite meshes, although I hear there's some progress being made on that. So for this effect, we were keen on retaining the same mesh fidelity as the rest of our environment. So the approach that I took was to create our render targets outside of Niagara in a blueprint, and then assign them on both the Niagara system through a user parameter and on the material instance created and assigned on the static mesh component that renders the vines. So this way we're not using any Niagara renderers, and we are free to use nanite meshes the usual way. Now, the thing is, when you use Niagara renderers, you can bind emitter values to the material instance through them. I needed to set a few of these, but without having a renderer, so I needed to devise a new method to do so. Niagara system user parameters can take objects of any type, so I added one and fed in the material instance that I created earlier. And then I wrote the material instance dynamic Niagara data interface that I mentioned earlier to set arbitrary values on it by material parameter name. In this screenshot, I'm setting a few scalar parameters, but it also supports float fours. And I'm glad to say that it's been adopted by the Niagara team, so it should land in UE 5.7. And in terms of material logic flow, that looks like this. So we take the vertex we are working on, we look at the branch pivot and use it to identify a chain it belongs to in the metadata render target. Then we identify the branch node index range, interpolate between this index range based on how far along the vertex is located in that chain, and sample the node position, normal, and tangent. That will then position the vertex relative to the PBD node transformation. The difference between this newly computed vertex position and the non-animated position forms an offset. Since all of our logic runs in local space, we then transform that into world space and finally feed it into world position offset in the material. Let's have a look at some results. So with the fundamentals of the solver, this is how far we get. It's already nice, but we can definitely add some more features to it. At Rare, we like to make our worlds feel grounded and dynamic, and one of the contributing aspects to that is our wind system. At a basic level, it's just a uniform global wind direction vector, which changes over time. It's a value that we can retrieve anywhere in blueprints, materials, in Niagara. If we plug it into the simulation, we get quite disappointing chains, like these are very straight and boring. Really, the quality of the results of a physics simulation depends on having quality inputs. So to get more interesting motion, we wanted to sample, or to get different values of wind at each node. If you think of real life, wind is not uniform, so that's what we want. So after initially experimenting with sampling some fractal Brownian motion functions at every PBD node, I ended up preferring just sampling a Perlin noise 3D texture using the PBD node's coordinates and also panning the texture over time. This has helped to reduce repetitive patterns and also algorithmic complexity. The texture sample value is then multiplied with the global wind direction vector and applied as an external force to the nodes in the simulation. And now it looks like wind is sort of traveling through the vines. If instead of this you had a 3D wind fluid simulation, you could sample that instead, of course. Another addition I made was to give the option to specify different mass values for different nodes along the chain. By using a set of mass curves, we identified the curve that is authored for the closest matching chain length and sample the curve on the GPU to assign the mass to the nodes themselves. Mass will control how much a node moves when forces are applied, but also when solving constraints. For example, with a length constraint, if two nodes with different mass values are linked together, the one with a higher mass value will show more resistance to moving than the one with a lower mass value. The correction value is then not spread evenly, but instead computed as a ratio of the two masses. Let's talk about collisions. So we can add collisions by sampling the global scene sign distance field through the collision query Niagara data interface to push nodes out of overlaps onto the surface of the meshes. Colliding with skinned animated characters is also possible. I've set up a few collision spheres on this character skeleton. These collision spheres can be queried with the built-in rigid mesh collision query Niagara data interface, which will find the ones within the bands of the emitter. Then Niagara provides some functions to push nodes out of intersections with these collision shapes along the closest surface normal. But it only gives you the current intersection state. It didn't really handle fast-moving collision shapes too well. And that issue is called tunneling. So if you have a moving collision sphere like this, which will go through a PBD node over the duration of one frame, we actually only have discrete times at which to evaluate the position of the collision sphere. So in reality, it will be here on one frame and then there on the next frame. At neither of these frames, we overlap with the PBD node to push it out of the way, so we can't detect that. We could use substepping between the previous and current frame positions of the sphere, like so, and push the PBD node out. But it's quite unclear how many times we should substep to get a good coverage. And the more we do, the more computational cost of evaluating the collisions at each position increases. Even with what looks like a decent coverage here, when we pushed the PBD node, it didn't actually go far enough. So instead, I implemented a swept sphere collision algorithm to take the sphere at frame n and n-1 and make a capsule of it. Capsules are easily defined analytically. Then we can evaluate whether the PBD node overlaps with the capsule, and if it does, we can push it out towards the closest surface. It doesn't actually matter how fast the sphere moves over the duration of one frame. We'll always be able to cover the entire volume it has moved between the two frames. Other collision shapes can be handled as well, of course, although they're not quite as straightforward to implement. So far, we've just pushed the PBD node along the surface normal. But if you think of how the collision sphere is moving through, you'd kind of expect the PBD node to inherit some of that velocity. So by biasing that vector a bit in the same direction as the collision shape movement, we get a better result. And then finally, it's also easy to add friction to the simulation by dampening the forces applied to a node when it collided with something on the last frame. A physics simulation can be a bit of a black box at times, so building ourselves good debugging tools can be invaluable. I already showed the character collision debug visualization earlier. In this video, you can see the per node wind noise forces being applied in green, alongside the static and current position of the PBD nodes in blue and red. And this is possible using the Draw Debug Niagara data interface. I mentioned earlier the simulation doesn't use particles, but we can spawn particles for debugging, and then move them to the same position and orientation as the PBD nodes in the simulation, and then visualize them with gizmos. With Niagara particles, we can now also rely on the very handy Niagara debugger tool to look at values on the PBD nodes, like whether it's colliding, what its mass is, or anything we want, as long as we copy their values onto the particle properties. Let's talk about performance. The graph at the bottom here, it comes from a PIX GPU capture on an Xbox Series X, and it represents all the function calls invoked when running through the shader. I don't expect you to read the text in them, just look at the sizes of the blocks. The size of them, it represents the amount of instructions, amount of cycles their instructions take. Remember that we are using an iterative solver, so we're not just going from the left to right along this diagram. We're actually looping over some of these instructions many times. So optimizing bottlenecks, we find here, will make a big difference. Using the asset I've been showing throughout this presentation, which has 53 vines of varying lengths, performance didn't look too great with 1.88 milliseconds as a starting point. But the bottleneck was quite obvious. We're stalling on worlds sign distance field texture fetches highlighted here. It's a bit small, so let me zoom in. Sampling the world's sign distance field for the environmental collision on every node, on every iteration, is quite costly. If we only sampled it on the last iteration, it might invalidate some of the PBD length constraints during that frame. However, they will be rectified in the next frame. And in practice, it gave us acceptable results. So doing less work is more efficient. So that's an easy, pragmatic solution that we've adopted. Next, if we actually look at the functions in play, we can notice that these two chunks look pretty similar. It turns out that the native collision query Niagara data interface evaluates the sign distance field's distance twice, once to return the distance and once during the computation of the surface gradient. So by merging these two functions together, we can avoid an extra evaluation. And then on the left-hand side, we can see a repeating pattern of these pink and green chunks. These are the actual sign distance fields texture samples to compute the gradient. There are 6 of them, as the engine uses central differences as the algorithm to compute the gradient. And it will need to sample in the positive and negative direction on all 3 axes around the current sample to compute the gradient. If we switch over to a forward difference algorithm, we can get rid of half of these samples. And together with the last 2 optimizations, we've gone from 8 texture samples to 4 for every node, which makes a big difference as it shrinks down. Finally, we also found it acceptable for our assets to not be longer than 32 nodes per vine. So we were able to enable wave 32 on our dispatch, which increased the wave occupancy and allows us to run more instances of this effect in parallel to maximize the GPU utilization. And now the cost is 0.22 milliseconds. And when we have 10 instances of this effect, it barely moves the needle because we can go wide on the GPU. As I said at the start, this is R&D work, so these numbers are not final. We may find further perf improvements or change how this is set up. But for now, this is in a good enough place to carry forward. Moving on to lessons learned. We've been looking at the performance costs of nanite deformation in general and found that nanite incurs a high cost when doing vertex deformation. This is due to working with a visibility buffer. The vertex shader logic is executed on a per pixel basis, but not just once, as it has to compute the value for the 3 vertices in the triangle before calculating the barycentric coordinates to perform world position offset and use that as the input to the pixel shader logic. But that's not the end of it, as the engine needs to compute the previous frame position values to be able to generate motion vectors. So it needs to do this for 3 more vertices. So we will run the vertex shader at least 6 times per pixel per nanite raster pass. With this effect, we've moved a lot of our computational work into a compute shader that only needs to run once and cache the results in a render target. These are then sampled in the vertex shader passes, but it reduces the performance impact a lot. One of the things that caught me was that nanite meshes started stretching triangles in unexpected ways when deforming it. Thankfully, there's now a setting in Unreal to on the mesh assets to specify a maximum length that an edge can have to reduce this stretching. If you set it to the smallest bending angle, bending length a mesh can undergo, we get rid of these issues. And then one of the great advantages of building a system like this in Niagara is that it's VFX artist and tech artist friendly. They can easily start expanding on the simulation tech. They have lots of built-in modules at their disposition to add flourishes. I didn't need to build any extra authoring tools for them. In terms of future work, finding ways to alleviate the serial nature of the solver would be a good idea. Maybe by solving positions at a coarser level first, and then solving intermediate positions in parallel. So far, I've only taken care of integrating linear momentum, no angular momentum. That would add some natural twisting motion, which could be a nice addition as well. Having multiple instances of the same material instance would reduce the amount of Nanite raster passes. This should be possible by sharing the simulation output render target across multiple instances. It's already possible to pin nodes down, but there's not great control over which ones. So adding a bit of tooling to let artists pick which ones would allow them to create interesting scenes. Structures with multiple branching directions instead of a single chain would also be quite interesting, I think, to build other type of foliage. This is a prototype, but you can see that it's more like a tree or a bush structure where multiple branches are connected to the same parent branch, either at the tip or even partway through. As the red sphere pushes nodes away, we can observe some organic motion emerging, as the connected branches are also moving along now. This version also features angle constraints. So when a branch will return back towards their original angle relative to their parent. This way, the entire structure returns to the original configuration when we've stopped disturbing it. But you could expand this further by being more stateful and having branches snap when pushed too far, or at least stay bent in a certain direction. I think there's some exciting opportunities in this space to make for more interactive environments in which players can feel truly immersed. That wraps up my talk on interactive Vine. So I want to thank my colleagues Andrew Catling, Emmett Green, Brian Smith, and Shannon Webster for their contributions. If you have any questions, you can ask me now, or you can find me after the talk as well. Thank you.